The next reaction that we're going to look at is the hydration of alkenes. So happens when an alkene reacts with water in acidic conditions. And the product of the reaction is an alcohol. So we saw that when alkenes react with hydrogen halides, the product was an alkyl halide. And now we're going to learn how to make alcohols. And we're going to see that the production of alkyl halides and alcohols is something that we're going to use over and over again throughout the year, basically. And these are fundamental reactions that we need to really understand how they work. Okay? So, again, I'll start off using 2,3-dimethyl 2-butene. And this time I'm going to react it with water in the presence of an acid catalyst. And when I do so, I produce an alcohol. So this is an addition reaction. Notice I've added essentially water across the double bond, hence the term hydration. I've hydrated an alkene, I've added water to it, HOH. And you'll also notice in this particular example that the two carbons are equivalent in terms of their addition. So in that first step, hydrogen could add to either carbon. Now, before we get into the regiochemistry of the reaction, let's talk about why we have to have an acid catalyst in this reaction instead of just water. Remember, water is HOH, so just like HX, HCl, HBr, water is HOH, and therefore, why isn't it that water doesn't just react with alkanes in the same manner that a hydrogen halide reacts with alkenes? Well, the simple answer is that water is too weak of an acid to protonate an alkene. And what that means is that hydrogen-oxygen bond is too strong in water relative to that of an HCl bond or an HBr bond. So how do we make a stronger acid? Well, if we take water and we add some acidic source from a strong acid like sulfuric acid, for example, in a catalytic amount, then we can generate the hydronium ion. So we get H3O+. Now, the hydronium ion is a much stronger acid than water is. And even though it may be a little bit weaker than HCl, it's still a very strong acid. And therefore, it's going to react in a similar manner as HCl or HBr. And so we can take a look at the mechanism of this reaction and see that, again, if we're taking 2,3-dimethyl 2-butene, reacting it now with the hydronium ion. I'm going to draw the hydronium ion like this. So I'm highlighting the H hydrogen-oxygen bond, and then the oxygen has two more hydrogens attached to it, and it has a pair of non-bonding electrons, and it has a positive formal charge. So now what happens? Well, again, the pi electrons, the HOMO pi electrons of the alkene attack the sigma star orbital of that oxygen-hydrogen bond, and once that occurs, you start to form a bond between one of the carbons and hydrogen, and the oxygen then accepts the pair of electrons. The result is you get a carbocation, right? So in this particular case, it doesn't matter which carbocation forms. I'm going to draw the carbocation on the left-hand side. So notice the hydrogen went to the carbon on the right. The carbocation goes to the carbon on the left. It's a tertiary carbocation, so it's a relatively stable carbocation in terms of carbocation stability. And now what else do we form? Well, those pair of electrons go to the oxygen. Now the oxygen has two lone non-bonding pair of electrons, and it becomes neutral, and we get water back. Now notice water has two pair of electrons. It is a nucleophile. and that nucleophile can attack the carbocation. So the pair of non-bonding electrons, which happens to be the highest occupied molecular orbital pair of electrons, is going to attack the LUMO carbocation. And what do we end up getting? So let's think about what we get, because this is where students commonly make mistakes. They simply say, oh, okay, I need to produce an alcohol, and therefore I'm going to just put an OH there. But notice, what's bonded to the oxygen. I have two hydrogens. There are two non-bonding pair of electrons. One of those non-bonding pair of electrons is attacking the carbocation, and it's going to form that bond between carbon and oxygen. The other pair of electrons is still there. So we still have two oxygen-hydrogen bonds. We still have a pair of non-bonding electrons, and now we have a new carbon-oxygen bond. And of course, if we calculate the formal charge, that oxygen has a positive formal charge. I have to get rid of that formal positive charge. And so what happens is, what I can do is I can simply, if I remove one of those protons, then I can form my alcohol. How do I do so? Well, this is called an oxonium ion, and oxonium ions are very acidic in nature. The oxygen's withdrawing electron density away from that hydrogen, and therefore if I have this in an aqueous solution, it's very easy that I can deprotonate it. Water can deprotonate it, and I end up with my alcohol as my product, right? So notice the pair of electrons from that oxygen-hydrogen bond go to the oxygen. I've highlighted those in red. Also notice what happens to the water. Well, that water removed a proton. In other words, the water got protonated. And so what we end up generating is another hydronium ion. So we regenerate the hydronium ion in the process. That's where the acid catalyst comes in. I need a catalytic amount of a proton source, because that proton source that can then be used in the first step, protonation, which then gets used up, but then gets regenerated in the very last step. So now it can be used again to protonate another alkene. So that's kind of a similar mechanism to the addition of hydrogen halides, but with an additional step in that deprotonation and reformation of the acid catalyst. All right, so what about regiochemistry, regioselectivity? Well, it happens that since the mechanism is pretty much the same, the regioselectivity is also the same as that of the addition of hydrogen halides. So for example, if I take 2-methyl-1-butene and I react it with water in the presence of an acid catalyst, so this is typically how you'll see it written. Water water over H3O plus. So understanding H3O plus is the acid catalyst. Sometimes you'll just see H3O plus in the as a reagent, right? And of course, now we have to think about regioselectivity. If we look at the two different carbons, the carbon on the left would form a tertiary carbocation, the carbon on the right would form a primary carbocation. So certainly our intermediate would be a tertiary carbocation. Then water would attack it, and then upon deprotonation of that oxonium ion, we would get our alcohol, 2-methyl-2-butanol. 2-methyl-2-butanol. Now, we can also do cyclic alkenes, right? Reacting 1-methyl-1-cyclohexene with water in the presence of an acid. Again, we evaluate the two carbons. The carbon on the left would produce a tertiary carbocation. The carbon on the right would produce a secondary carbocation. So the tertiary carbocation would be formed, water would attack it. Upon deprotonation, I would yield my alcohol, 1-methyl-1-cyclohexanol. and that is the hydration of alkenes.